Next Lewis structure, carbon dioxide, CO2. Okay, so as we've been talking about, carbon dioxide is always carbon dioxide, not dioxide carbon, and now we know the reason. Carbon is the central atom, so no problem. Valence electrons, carbon has 4, group 4A, oxygen has 6, group 6A. So valence electrons would be 4 from carbon plus 6 times 2 for oxygen. So that's 4 plus 12, that means there's going to be 16 valence electrons, or if you divide that by 2, that's going to be 8 pairs of electrons. Okay, so I'm going to go faster through this, and definitely feel free to pause it and think about it before moving on if you need to, but it's going to be 16 electrons and 8 pairs for carbon dioxide. We're going to put our carbon in the middle. We're going to connect the outer oxygens to the middle with a sigma bond, so it's going to look like this initially. Each of those lines is a pair, so of our 8 pairs, we then have 6 pairs left. We're going to put electrons on the lone pair electrons on the outer atoms first, and if there's any left over, we'll put them on the inside atom. Now we have 6 pairs of electrons left to put out, and you want an octet when possible. So we're going to put 3 lone pairs on the outside oxygen on the right and 3 on the outside oxygen on the left. This is initially what we get. And if you stop and think about this structure for a little bit, your oxygens both have an octet. They have 3 lone pairs and a bonding pair for 4 pairs total. That's an octet. The oxygens here are happy, but the carbon only has 2 pairs. And carbon really wants to have an octet. It wants it so much that it's actually going to steal electron density from the outer atoms and give it back to itself. So this is the first time that we've seen a new type of bond happen, and it's only because carbon is not happy. Carbon needs an octet. So what we're going to do is we're going to share 1 lone pair from each oxygen with the carbon. And you can see now this new structure right here. This is a special kind of bond. The black bonds on the bottom, those are those sigma bonds, all right, we saw earlier. But when you make a second bond, which is the red bond here, those are called pi bonds. Pi is the symbol you've probably seen from math, which looks like that. This is not 3.1416, blah, blah, blah. That has to do with circles and stuff like that. This is a symbol for this kind of bonding. So a pi bond occurs after a sigma bond is made. It's usually to make the central atom have an equivalent octet. And if you look at our new structure now, carbon is in an octet. It has 1, 2, 3, 4 lines around it. That's 4 bonding pairs. That's an octet. And really, oxygen is okay here too. We stole a lone pair, but oxygen now has 2 bonding pairs and 2 lone pairs. So each of the oxygens has an octet as well. So carbon says, hey, oxygen, you got to share your electrons with me. And carbon's tough enough that this actually happens. So if your central atom doesn't have an octet, it's going to steal essentially a lone pair from the outside atom and turning it into a bonding pair. And the second bonding pair is what they call a pi bond. This black line and red line combination I will call a double bond. And just realize it in your own mind that a double bond has a sigma bond and a pi bond. So 1 sigma plus 1 pi gives 2 bonds. That's what double bond is. Double bonds are very common. All right, there's lots of examples. You even see sometimes some triple bonds. Here's just a couple examples, and we'll look at some more here in a little bit and of what can happen. But we'll see lots and lots of multiple bonds. It's no big deal. They are very common for carbon, nitrogen, phosphorus, oxygen, and sulfur. But they can also occur sometimes with metals, which is a future class we'll talk maybe about. Lots and lots of examples of these pi bonds being made. Let's look at sulfur dioxide. Sulfur dioxide is 1 sulfur and 2 oxygens. Well, central atom, again, first one listed, sulfur, no problem. Oxygens will be on the outside. Valence electrons, both sulfur and oxygen are group 6, so 6 times essentially 3 is 18. Divide that by 2, 9 pairs. Sulfur in the middle, oxygens on the outside. Put the bonding pairs down first to connect the oxygens to the sulfur. That's 2 of the 9 pairs. Then put the lone pairs around outside atoms first, and if there's any left over, put them on the inside. So you can see in this structure right here, the oxygens have a filled octet, 3 lone pairs and a bonding pair. The sulfur has 1 more pair left over. It goes on the middle. So a question to ask yourself right now, does the sulfur have a filled octet? And if you said no, you are absolutely right. Sulfur, like carbon, wants to have 4 pairs around it. An octet means 4 pairs. Each one of those lines and double dots is 2 electrons, so it wants to have 4. So you're going to have to make a double bond somewhere. But the question is, do you take it from the left oxygen or do you take it from the right oxygen? You have a choice where that pi bond is going to come from, all right? As a scientist, you think about, well, is there an energy difference between having a lone pair from being used for a double bond on the left versus the right? And the question is absolutely not. There's no energy difference whatsoever. So this leads to a really interesting phenomena that happens sometimes with multiple bonds. You have a choice as to which structure you're going to draw. Now, this down here on this big thing, this is showing the 2 possibilities. So you can see the left structure, the red line is between the left oxygen and the sulfur. On the other hand, the right-hand structure, the red line is between the right-hand oxygen and the central sulfur. Now, both of those structures there have octets around all the atoms, all right? The oxygens have 1, 2, 3, 4, either 2 bonding and 2 lone pairs, or 3 lone pairs and 1 bonding. And sulfur has 3 bonding pairs and 1 lone pair. So everything here has an octet. There's no energy difference between them. So this comes up to something called resonance. And resonance is when you literally have a choice where the double bond is going to be. And if there is no preference energetically for one side or the other, then these structures are going to they're going to be both of them together. So as a chemist then, sometimes you'll write this kind of double-sided arrow right there, showing that these are resonance forms. They both contribute. Now in reality, this molecule probably has half of a pi bond on the left and half of a pi bond on the right. It's a hybrid of these 2 structures we've drawn. But our limitations of Lewis structures prevent us from really doing that with any kind of justice. So resonance is kind of the background thing you should think about when it comes to double bonds. If the double bond can move around with no energy difference, then you're going to have these resonance structures. In this question, we're seeing 4 Lewis structures for N2O, dinitrogen monoxide, and one of them is incorrect. And the question is, which one is incorrect, or are they all okay? This question also goes back to the octet. You want to look for a structure which doesn't have an octet or maybe has more than an octet. And if you look, for example, at number 1, the nitrogen and the oxygen both have 2 lone pairs and 2 bonding pairs. So for a total of 4 pairs, that's okay. So the N and the O on the outside are okay. And the middle N is okay as well. The middle N has 4 bonding pairs and no lone pairs, but it's got its 4 pairs. That's what an octet is. So number 1 looks okay to me. Number 2 and number 3 are similar. Those are both with a triple bond, by the way. The triple bond, like this one right here, comes around from having 1 sigma and 2 pi bonds. But regardless, for this one, thinking about octets, the oxygen on the far right has 3 lone pairs and a bonding pair for 4 pairs total. That's okay. The middle nitrogen has 4 bonding pairs. Triple and a single would be 4. That's that's legit. And the left-hand side nitrogen, 3 bonding pairs and 1 lone pair, well, that's 4 pairs as well. Structure 2 is okay as well. Number 3 is very similar to number 2, and if you analyze the different atoms there, you'll find all of them have an octet, so number 3 looks okay. Number 4, however, if you look at the central nitrogen, how many bonding pairs are around it? And if you count it, there's a triple on the left and a double on the right. 1, 2, 3, 4, 5. Uh-oh, this is the first time we've seen an atom with more than 4 pairs. And for nitrogen, you never want to have more than 4 pairs. And we're going to talk about this here in a little bit. So answer 4 is incorrect because nitrogen has more than an octet. And we're going to see that some atoms can go more, but nitrogen and carbon and oxygen, for that matter, can never have more than 4. So answer or structure 4 is incorrect because the central atom, too much electron density around it.